In this video, we'll go over some of the theoretical aspects of vectors in linear algebra that are going to relate later to how we want to solve systems of differential equations, and we'll see how this theory is sort of parallel to what we've already discussed for the theory from second-order equations last chapter. So let's think back to this theory from second-order equations. How do we go about solving these equations in the first place? So if we had a random second-order linear constant coefficient homogeneous equation, something like that, how do we solve this? Well, we started by guessing e to the rt's possible solution, plugging that in and using the roots of our characteristic equation to then determine what would be our solutions here. That was only the first part of the process. Once we had these two solutions, whether they were real and distinct roots or complex roots or repeated roots, we then had to verify that this actually gave us a full general solution. So we get to a solution of the form c1y1 plus c2y2. We want to say that this is a general solution. And how do we do that? We use the idea of linear independence to do so. Right? We wanted to see, okay, are y1 and y2 independent? And if they are, that gave rise to a general solution. What was the idea there? Well, I wanted to look to see if it was possible to write 0 in exactly this form. So linear independence asked, can I write c1y1 plus c2y2 equals 0 without picking c1 and c2 equals 0? If this was not possible, they're linearly independent, and if they're independent, this is a general solution. We also, on top of that, had the Wronskian, which let us check to see if things were linearly independent or not. That was this y1, y2 prime minus y1 prime, y2 being non-zero, and we'll see how that connects a little bit later on. But as of now, I want to get back to the idea of linear independence, seeing when you can add these together to get 0, and if you can't, they're linearly independent, and then things are good from there. Now let's tie this all back to vectors. So if I have vectors, we have a very, very similar definition for linear independence. If I have a collection of k vectors here, this v1 through vk, we say they're linearly independent. The only way that I can add them together with constants to get 0 is by picking the constants themselves to be 0. This is identical to what we had for linear independence for functions, that we had like this linear combination, this c1, v1, c2, v2, etc., and add it together to get 0. And if there's a way to do it without picking all the c's to be 0, they're linearly dependent, like what says here on the bottom. This is the same definition, and the same sort of ideas apply. Right, we had our trick before where we had two functions. They were linearly dependent if and only if they were multiple of each other. The same holds here. So if I have two vectors, they are linearly dependent if and only if they are multiples of each other. So for example, right, the vectors 1, 2, and 4, 5 are linearly independent because they are not multiple of each other, but the set 1 minus 1 and 4 minus 4 are dependent because they are multiples of each other. And this is just for two vectors. For more than that, the process gets a little more complicated. So here we have two different sets of three vectors, and I want to determine if they are linearly independent. If you look over the set right now, you will see that in each individual set, no vector is a multiple of any other vector. However, because we have more than two vectors, that's not enough to guarantee linear independence. Let's work with the first set first and see what we have to do. So if I want to figure out if they're independent, what does that mean? Well, it means I have to figure out if there are a choice of constants, c1, c2, and c3, so that when I take c1 times the first vector, 3, 1, 1, plus c times the second vector, 1, 0, minus 3, plus c3 times the third vector, 5, 2, 1, can I get the vector 0, 0, 0 out of this without picking c1, c2, and c3 all to be 0? Well, I can rearrange a little bit. I can put these together into a sort of single vector expression. That looks something like 3c1 plus c2 plus 5c3. Combining all of the first components of every vector here, similar for the second and third, that should equal 0, 0, 0. But what does this look like? This is exactly a three-variable linear system of equations, which we dealt with in the previous section. Our variables here now are the c's, but our equations here are what we've seen a million times before already. 3c1 plus c2 plus 5c3 equals 0, c1 plus 2c3 equals 0, c1 minus 3c2 plus c3 equals 0. This is a very standard problem we can now solve. We know how to solve this. We can solve this via row reduction. Standard 3 by 3, three variables, three equations, we can solve this. So we can put this into augmented matrix form and row reduce from there. So augmented matrix that we start with is going to look something like this, and we can row reduce this to try to solve. I'm not going to carry out the full process here. If you want to review this, you can. What I'm going to do is I'm going to swap rows 1 and 2 to put that 1, 0, 2 in the top. I will cancel that down, and I'll end up with a 1 in that middle spot of the matrix, so I can use that to cancel below it, and that'll result in the following matrix. Now, if we were to read this off as equations, I would get that negative 4c3 C3 is 0, C2 minus C3 is 0, and C1 plus 2C3 is 0. And since we have this first equation here, everything's going to have to be 0. C3 is 0, therefore C2 is 0, therefore C1 is 0. And then these are linearly independent because the only way to make these all add to 0 is by picking C1, C2, and C3 to all be 0. Now, before we do the second example, let's look back at what we did and see if we can figure out ways to make this process easier. What was the key at the end of the problem? Well, the key at the end was that I had this equation, minus 4C3 is 0. In fact, I had to use all three equations, and all three equations matter at the end of this problem. The key point was I have pivot elements in all three of these spots. If I divide that minus 4 by minus 4, I'll get to 1 there, and I will get exactly a 1, 1, 1 down the diagonal for my pivot elements. Every single column here is a pivot column, and that forces me to make them all to be 0 to solve this all out, because the last question told me that C3 has to be 0. Once C3 is 0, I get rid of that third column because it's not going to matter anymore. Then C2 has to be 0, and up the chain. So a pivot column in every column on the variable side means that they're linearly independent. We only get the one solution. All columns as pivot columns means it's linearly independent. Point 2 with this is this last column. The zeros never change. 0 stays 0 stays 0, so I can ignore the 0 column at the end. It's not going to affect my result. And the third point is how we started the problem. So we started with this matrix right over here. Where did this come from? Well, if I look back at the problem itself, those three columns here are exactly my three vectors from the very start. So I don't have to go through this whole formal process of setting up the equations going from there. I just know that if I want to find independence, I take those vectors, put them as the columns in a matrix, and row reduce from there. So with that in mind, let's now look at our second example here. Those are a set of vectors. And based on what we just discussed, we can jump from here right to needing to row reduce the following matrix. We don't need the zeros on the end. They're there and they're implied, but they're not going to change, so we can leave them alone. And we just take those vectors, put them as the columns, and go from there. We row reduce. Again, I'm not going to do the whole process out here, but what you would get from this is you would use the 1 to cancel below it, and then you could divide the middle row by 5, and then use it to cancel the row below it. And if you do all of that, you will end up with the following. What do we see is different here? Well, in this case, now row 3 is all zeros, and column 3 is not a pivot column. That means that C3 here is a free variable. And then the equation we have left over after that are 2C2 plus C3 must be 0. Remember, the zeros are there, but they're implied. And then C1 minus 3C2 minus 2C3 is 0. So if I pick, for instance, C3 to be 2, then C2 needs to be minus 1 because 2C2 plus 2 is 0. And if those are both the case, then C1 is going to be 2C3 plus 3C2, which is 4 minus 3 or 1. So what that then tells us is we can pick C1 to be 1, C2 to be negative 1, and C3 to be 2, and that will add to give us 0. So as a quick check of that, if we take 1 times our first vector, minus 1 times our second vector, plus 2 times our third vector, and add that up, you'll see we get 1 plus 3 minus 4 is 0, 2 minus 4 plus 2 is 0, and 1 minus 1 is 0. We have found a linear combination that adds to 0, and therefore these are linearly dependent. So 2 examples, one that shows how you get independence, one that shows how you get dependence. What have we learned from this? The main idea here is how linear independence works and how you can find it by row reduction. So what do? We take the vectors and we put them as the columns in a matrix. We then row reduce this matrix. Again, we don't need to put the zeros on the additional column because they're not going to change. We can sort of think of them there as implied and just not write them down every time. So we're going to row reduce this matrix and look at the pivot elements and pivot column. If every column in this matrix, ignoring that 0 column on the far side, if every column is a pivot column, then the vectors we have are linearly independent. If there is a variable column that is not a pivot column, then they're linearly dependent, and the variable that is free can be written as a linear combination of the other vectors. We will see soon why linear independence is so important, why it matters so much for what we're trying to do here, but as of now, we just want to know how to find it. So question to consider, and try to answer this on your own before moving forward. What is the largest possible number of linearly independent 3-component vectors that one can have? So if I give you a set of 3-component vectors, how many of them can you have that are linearly independent? Not have to be, but is there a maximum on how many you could have and still have them be linearly independent? Once you think about that, think about the same thing for n component vectors. If I give you n component vectors for any number n, a single number n, what is the largest number of vectors you can have and still have them be linearly independent? So give that some thought, and then that's going to be the key to going forward to seeing why this idea of independence matters to us so much.